Hello, today we are talking about area, and this area is going to be between a curve that we've been given in the x-axis, and we are going to evaluate that by using a definite integral. So, talking about the definite integral first. So when we're asked about finding a definite integral, the value will always be signed. It will be positive or negative. However, if you are specifically asked to find area, that entity, that value will always be positive. Okay, so there's a difference. A definite integral could be negative, whereas if the question asks you to find an area, that will always be positive. So let's look at the picture that we have right here. And in this picture, we have a shaded region called S, and it's bounded. Okay, we always have to have a region bounded by something, and it's bounded by the line x equals a. It's also bounded by the line x equals b. It's also bounded by the curve f of x. And it's not quite finished being bounded right now because this would go on forever down past the x-axis. However, we are also bounded by the x-axis. And once I draw all those in, I should have a region. And that region is shaded in your picture, and it's labeled S. So before we even start finding this area, we are going to draw a rectangle in here, a very specific rectangle, in fact. And we want our rectangle that could be used as a Riemann sum. Now we've worked with Riemann sums before, so I'm just going to draw in a rectangle. It doesn't have to be anywhere particular, but I would like to see a rectangle. I generally shade it in so I can tell exactly where my rectangle is. And then if I were to find the area of this rectangle, the height of my rectangle would be whatever y is, or in this case, f of x. So however you want to talk about f of x, you can call it y. And then we also have a width for this rectangle, and the width of this rectangle would be whatever our change in x is, or dx. So then, to find this area, we would use a definite integral. Now this definite integral, what it's going to do is it's going to add up all of these rectangles as our dx gets smaller and smaller and smaller and smaller. So our definite integral is actually an accumulator, and it's accumulating all of the areas of these rectangles. So our definite integral would start at a, our first x value, and it would go all the way to b. So I'm adding up all the rectangles starting when x is a and going until x is b. Then I would be finding the areas, and I would have f of x, which is our y value, and then I would be multiplying by the width, which is dx. So now the next thing on this handout says, in this definite integral, identify each item as an x value or as a y value. So I'm going to start with the bounds. The bounds in this case are a and b, and those were x values. So this is an x value, and b is also an x value. Now we're on f of x, and f of x is this, which is a y value. So our f of x is actually a y value. And then my change in x, or my dx, this is actually an x value as well. Although it is a change in the x values, we're going to call it an x value. So this is us identifying everything. And what we really need to notice is the blue part is a y value. However, all the other things are x's. So whenever you see a dx right here, this should be an x value, this should be a y value, and the blue should be a y value. So if you see the dx here, the a should be an x value, b should be an x value, and then what I'm finding the antiderivative of should be a y value. So let's try one. Moving on to our first example, like that so we can see it. We are finding the area bounded by y equals x squared, x equals 2, and the x-axis. So again, I'm going to start by drawing in my rectangle. So here's my little rectangle that I draw in to represent the area of one rectangle that I'm finding. And my width, let's talk about my width first. The width of my rectangle is a change in x values, but the height of my rectangle is an f of x value, which is a y value, which in our case we actually know what it is because y is x squared. So now we should be able to set up our definite integral. So again, my width is dx, which means I'm going to have an x value here, an x value here, and I'm going to have that my width is dx. So what I'm going to do now is I'm going to fill in my x values. What is the first x value that I want to use? And in this particular region, the first x value is right here, which is at x is 0. And then the last x value I have is 2. That was one of my boundaries. The region was bounded by x is 2. And then I'm going to have what my height is, because now I need an area. I've got my width there already. That's my dx. And my height is my function, which is x squared. So at this point, I need to actually find this area. Sorry, I do need to adjust and actually identify these items. So my dx is an x value, and my 0 is an x value, and my 2 is an x value. My x squared, however, is actually a y value. Now I need to evaluate this and get a number for my area. And for right now, while we're working with area and learning this, we're going to go ahead and just do our definite integrals with our calculator. So using our calculator, I'm going to go to fint, which I think is 9 on everyone's calculator. And again, mine is the old school form. The new school form is going to look exactly like we've already written it on the screen. So if you've got the old school form, we need to say, well, what's the function, which is x squared? And then what was our dx? Sorry, what was our d, our change in something? Our width was our change in x. And then I need to start when x is 0, and I need to go to x is 2. And we should get an answer, and our area is equal to 2.66, or in other words, that's 8/3, whichever way you like to write it is fine. It's all the same. So that's our first one that we did for area. So let's try this next one. It's the same idea, it really is. It's just a little bit different because of the way our region is created. When I draw in my rectangle, if I draw in my rectangle at the right end, my rectangle's right here, and the highest I touch is at y equals 3, and the lowest I touch is at y equals 1. However, if I draw a rectangle over here, the highest I touch is y is 3, but the lowest that I touch is the square root of x minus 2. Now my Riemann sum has to, my rectangle, has to be referencing the same height all the way across. And right here, the heights are different. The height for this rectangle is just 2 because it goes from y is 1 to y is 3. However, the height of this one is 3 minus the square root of x minus 2. That's that height. So I can do this with area and a definite integral, but I would need 2 separate integrals to solve this, and I'd rather not do that. So I'm going to erase what I have, and I'm going to draw a different rectangle. And if I draw my rectangle so that it's horizontal instead of vertical, then no matter where I draw this rectangle, at the left side I'm always on the y-axis, and on the right side I'm always on the square root of x minus 2. So this is actually the orientation that I want to have for this particular rectangle. Now with this particular rectangle I have a different height and I have a different width. Let's talk about my width first. My width was usually a dx. In this case my width is a dy. And now that I have this as my height of my rectangle, that height is an x value, right? That would be, my height would be an x, no longer a y, which means it's my x value with this relationship. So what I actually need to do first is get x by itself so that I have a function in terms of y. So to get x by itself, the first thing I would do is square both sides. So I'd have y squared is equal to x minus 2. And then to get x all the way by itself, I would add 2, and I get y squared plus 2. So that's really what my height is going to be every single time. Of my rectangle. The height of my rectangle will be x, which in this case is y squared plus 2. So I'm going to now set up my definite integral the same way that I did with the other one, except my bounds in the one I did just above, those were x values because my width was a dx. However, this time my width is a dy, which means my bounds should be y values. And again, if I want my rectangle to travel all the way from one end of my area to another end of my area, I'm going to have to go from y is 1 to y is 3. So those are my bounds. I start at y is 1 and I go to y is 3. And then I have my width of my rectangle in, it's dy. I need to now multiply by the height, which is y squared plus 2. So this is the definite integral to represent what the area of this will be. So a couple of things to notice. We have a y value here. We have a y value here. We have a y value here. And this thing is actually an x value. But when it's an x value, what variable do you see? You see y. Look at the one above. When I had dx, I will see an x right here. Even though that's a y value, this will be an x value and this will be an x value. So when I change the orientation of my rectangle, and my rectangle is now perpendicular to the y-axis, I should see y's in my definite integral and have a dy there. So we're going to go ahead and find this area, and again we're going to use our calculator. So we're going to go to fint and put in our function. In this case I'm still going to use x's. So x squared plus 2, even though I'm really doing dy's, it's just easier to use the x's. You can do y's if you would like. You should get the same thing. And we get 12.6 repeating. Let's write that down, sorry. Except that I put in, okay, never mind. So 12.6 repeating, you could also have made that into a fraction. I have a pen in my hand. Sorry, so then you could also change that into a fraction and you get 38 thirds, and either way will be the same. Next example that we have, now we are trying to find the area that is bounded by this parabola. The line x is equal to negative 1.5, sorry, bad line, and the line x is equal to 1.5, and the x-axis. So this is an example where we can't just use one definite integral. And the reason for that is, I'm going to call this region A down here. Region A, when I find its definite integral, will be a negative value. So that's going to be a negative definite integral. Same thing for the one on the right. I'm going to call that region C. That will also be a negative definite integral. However, region B is going to be a positive definite integral. Now, we need to break this up, and we need to have a total of 3 definite integrals. Now, before I can even start, I need to find some bounds for my negative definite integrals. And this dot that I have is where the curve crosses the x-axis, and that's going to be one of my bounds for the first, my integral, if that is area A. I also need to find one of the bounds for the region in C. So first thing I need to do is actually figure that out. Well, where does my parabola cross the x-axis? Well, it's where the y value is equal to 0. So working that out, I multiply both sides by 3/4. I add x squared to one side, and I take the square root. So I get that this happens at x is equal to -1, and this happens at x is equal to +1. So now I'm going to set up a definite integral for each of my areas, for each region. So I'm going to draw in a rectangle into my first region, just so I can see what I have. Do I have dy's? Do I have dx's? And I would go ahead and draw my rectangle like this, so that I know that my width in this case is going to be dx, and I know that my height is going to be y. And I know what y is. Y is 3/4 1 minus x squared. So region A will be a definite integral. Again, my width is going to be dx, which means my bounds here and here will have to be x values, and those x values are going to be -1.5 to -1, and then my height will be my y value, and that will be 3/4 times 1 minus x squared. Now, this region, when I find this area, is going to be a negative value, which I'm going to have to adjust for when I'm finding total area. So what I'd like you to do right now, I would like for you to do the setups for region B and for region C. So I would like for you right now to pause the video to find those two setups. So pause your video now, please. So here are my three setups. For B, my bounds go from -1 to +1 of 3/4 times parentheses 1 minus x squared parentheses dx. And my region C goes from 1 to 1.5, 3/4 1 minus x squared in parentheses times dx. So now what I need to do is actually evaluate each of these definite integrals. So we're actually going to do this together. I know that you could do it by yourselves, but I'm going to try and show you sort of a faster way. So we go into fint again, and what I'm going to do is I'm going to do 3/4 times my 1 minus x squared. And again, I'm using the variable x, and I'm going from -1.5 to a -1. So this should give me the definite integral for region A, and this is -0.2 -0.1875. Now when I want to find the next one, I'm taking the same definite integral, I just have different bounds. So I'm going to press second enter to bring the last line back up again. So I hit second enter, and exactly what I did just appears. And all I need to do is change my bounds. So I'm going to go from -1 to +1. So comma, +1, and then press the delete button to get rid of the rest of the stuff. And now I'm doing this definite integral from -1 to 1. And that gives me 1. Now we're going to do the same thing, second enter, to do our last region. And this region, we are going from 1 to 1.5. So again, even though you have multiple regions, it's not too bad to use your calculator to key them in and find the answers. So these are our three areas that we have, and again we have negatives. We're going to add the absolute values of them. So the total area is actually going to be 0.21875 plus 1 plus 0.21875. So we're going to add that all up. And when I add that up, I get 1.4375 as my total area. Please, if you have any questions, write them down on your paper. Now, the next thing we want to do is we're going to find the area between two curves. Now, before we were using the curve and an x-axis. That was pretty good. Feel pretty comfortable about that. Now we're going to find the area between two curves. So the first thing we're going to do is we're going to draw in a rectangle again. So here is our rectangle that we could use for a Riemann sum. And we need to figure out what kind of things that we have. Well, first of all, I think we're okay that the width of this rectangle is a change in x. So that's a dx. The question is, what's the height of my rectangle? Well, I kind of have two, and I'm going to combine them together. So this part of my rectangle, that height is a y value, but more specifically because I have two different functions here, that y value is f of x. When I look at my other one, down here, this is a y value, and that's g of x. But I need to kind of pay attention. My g of x, at this place where I drew my rectangle, is a negative value. So I kind of need to put them together and actually combine them. So this is actually, this height is going to be in total, is going to be f of x subtract g of x. That's actually going to be the whole height of that particular rectangle. Well, Miss Baird, there seems to be area above the x-axis, which would be positive, and area below the x-axis, which would be negative. So I get why you're subtracting here to make the rectangle actually longer. What if the rectangle wasn't where we drew it this time? Well, okay, let's draw it somewhere else. Now, you don't need to erase. You can leave yours written in however it is. But let me just show you what I'm talking about. What if my rectangle was over here? So again, my dx, I think we're okay that my dx is my width. And what we have is, from here all the way down to the x-axis is my y that is f of x. But that's not actually what I want for the height of my rectangle. I need to take out this height. And this height is from g of x. So does it make sense that the height that we want, that's drawn in black, would actually be the blue f of x subtract the red g of x. So that makes this height here is still the blue f of x subtract the red g of x. So let's go ahead and write what our definite integral would look like now. So our definite integral to find the area, again, our width, let's talk about our width. Our width is dx, which means my bounds here and here should be x values. In this case, our x values again are a and b. And then I'm going to have the height of the rectangle. Well, the height of a rectangle is actually its own little expression. In this case, it's the highest curve, the top of my rectangle, the furthest away from the x-axis, minus the lower curve, the bottom of my rectangle, the closest to the x-axis. So that would be the definite integral for that particular problem. So in example 4, we are trying to find the area of the region created by y equals x squared plus 1 and y equals x plus 3. So what I want you to do right now is I want you to write down what the definite integral would be. So please pause the video and work on that definite integral. Pause the video now, please. So this is my setup that I have right here to find my area. Now in this one I wasn't actually given the bounds, but I was capable of finding the bounds. In order to find the x values that bounded these two curves, I needed to set them equal to each other in order to find those bounds. So I set x squared plus 1 equal to x plus 3, worked that out, and I got x was 2 and x is negative 1. If you didn't get that, pause the video now so that you can work that out. Once I had my bounds, I needed to know how high the rectangle was. And for this one, the top of the rectangle touched the red curve, y equals x plus 3. The bottom of the rectangle touched the blue curve, y equals x squared plus 1. And I needed to subtract those to get the height. So the height of my rectangle was the red, x plus 3, minus the blue, x squared plus 1. And again, the width of my rectangle was dx. So I need to multiply by the width, and then my bounds were the two x values I found from negative 1 to 2. I could evaluate this using my calculator. And again, we should be okay at this. We need some parentheses though. X plus 3, we need to subtract parentheses x squared plus 1. So those extra set of parentheses right there are very important. Comma, x, comma, -1, comma 2. And I get 3. Okay, so my area is 3. The next style that we have is exactly what we did last time. Is the orientation of my rectangle is going to change. If I draw my rectangle like this, I have the same curve, the red one, minus the red one to get the height. However, over here, I would have this bound A, no, that's a D minus the blue curve. So I would have two different definite integrals because the top and bottom of my rectangles change depending on where I put my rectangles, which means I need to change the orientation of my rectangle to be horizontal. When I draw my rectangle horizontally, the right side is always the blue curve, and the left side is always the red curve, no matter where I put this particular rectangle. So this change in y is going to be the width of my rectangle, and now I need to find the height. So again, the furthest away minus the closest, or the one above. So this right here is my positive x, which is f of y. And then down here is my negative. I just have a little tiny bit right here. This guy right here is my negative x, which is g of y. So it's the same thing. We need to remember that with x values, when I go to the right, these are positive. That's the biggest. So I'm always going to take the right side and subtract the left side, which could be negative, and if not negative, it's definitely the smallest. So let's go ahead and write our definite integral for our area. So area is going to be, we now have a width of dy, which means my bounds should be y values. In this case, they are c and d. Lower bound goes on the bottom, which is c. Upper bound goes on the top, which is d. And now I need to multiply by the height of my rectangle, which will be the curve furthest away, which is f of y, minus the curve closest to the y-axis, g of y. So now we're going to try one. So if you go to the last page of your packet, we're on example 5. What I'd like you to try and do is find the setup for this definite integral. You can do this. So what I'd like you to do is find that setup. Pause your video now, please. So here's my setup. I drew in my rectangle. I noticed the width was a dy. So I have a dy as my width. And then I know I need to take the right side of the rectangle minus the left side of the rectangle to get the height of the rectangle, which would be the purple curve minus the blue curve. Now the purple curve I did have to manipulate a little bit because it wasn't in terms of x, meaning I had to get an x equals. So I went ahead and added 2 to both sides to get a y plus 2 as the x value there. The other curve, the blue one, the one I was subtracting, that's already in terms of x. So I knew x was equal to y squared. And again, little cues. I see a y right here. I should see y's in here. And this should be a y value. And this should be a y value. So everything should be clear about what variables you should be seeing within your definite integral. Please write down any questions that you have and bring them to class. And I hope you have a wonderful evening.